So, assuming that we have managed to compile our program, what usually gets created is a set of what are called .o or object files, and putting them all together in such a way that we can actually run it on a processor involves something else called the linking process. Now, when a program is written, right, or more importantly, when a program actually executes in the memory of a processor, it is occupying a large amount of memory within the overall memory that's available to the processor. And what we have out here is a breakdown of the main parts of a program that we need to be interested in, we need to know about in terms of how exactly a system works, right? And all of these terms that you see over here, there is something called the text, which is the actual code that needs to run on a processor, right? RO data and data, which are basically the variables that are being variables, or in some cases constants, read only data, right, that are used or declared as part of the program. There is one section called BSS, which basically stands for block started by symbol. It is some historical artifact why exactly it's called that way, but the practical matter is that the BSS basically stands for all uninitialized variables, things that don't need to have a value actually in the program itself that tells you what to initialize them to, but space needs to be allocated for them before the program can actually run. Right? So what's actually happening is that even though we created some object code, some .o code, a set of assembly language instructions, right, similar to what we already saw as an example, right, that by itself is not sufficient for a program to run. The very minimum that I need to do is take those instructions and copy them into the text part of whatever memory has been allocated for my program to run, right, so that I now know that these instructions are available starting at some particular place in memory. But apart from that, I have certain variables, right, and if they are sort of dynamic variables, they are function local variables, they need to go into certain parts of the memory which I'm going to call as the stack. If I'm using function calls like malloc in order to dynamically allocate arrays, they go into the so-called heap. If there are other variables that I declare and immediately initialize them to a known value, or maybe they are global variables, they go into the data segment. If there are others that are declared but not initialized, they go into the BSS. In other words, as you can see over here, there's a lot of data management that I need to do in order to actually run a program. Just the instructions alone are a small part of the overall program. What has to happen is that I need to take this machine code that I generated, which is a set of instructions, and modify it in such a way that, for example, the branches, the function calls and so on are all modified slightly so that they actually refer to physical addresses that are present within the system and not just some logical addresses that I have in my program. Now, why is this needed? Because when I actually create a program, I do not know the actual physical addresses at which they are going to reside, or even which particular member of the ARM Cortex family I may be running on, because the instruction set by itself is usually sort of compatible with multiple different variants of the family. It's possible that I'm not exactly running it on the same thing for which I compiled it to start off. So given all of that background, it becomes clear that there are two things that we need to do. One is that at compilation time itself, I may need to sort of take multiple different object files which contain different functions and put them together systematically to create a larger program. And then at actual runtime, I may need to sort of make sure that I load them into memory in a proper way so that they can all do their work and the code can execute while making use of the data that is present in all the other different parts of the memory. Now, in order to understand what exactly the linking process does, it's important to know that there are typically libraries that are present in every system, and a library in the context of a programming system or a computer system is basically a collection of pre-compiled code, right? In the context of C, right, we have when we start writing a program, we straight away assume that we can use functions like printf, scanf, puts and so on, right? While and for, of course, are keywords of the language. They are not function calls. There is actually, the compiler takes care of generating code corresponding to while and for and so on. But printf is not a keyword, right? It is something which is actually a separate function that has been defined somewhere, and when you call printf, you are actually performing a function call, right? And what has to happen in that context is that the program has to create space for a new function. It has to basically set up the stack, set up the variables required by that function, the arguments of that function, and then it has to perform a branch to the place where the code corresponding to that function is. Now, when we write a program, we don't write the entire machine code or even the instructions for how to actually implement printf, right? What ends up happening is that we just call printf and we assume that somebody has taken care of defining it for us. That is part of the so-called standard library, right? Similarly, there may be certain other functions like sine, cosine, network related functions and so on, which again we assume are available, but may be sort of specialized things that are not part of the standard library, standard C runtime, right? And these kind of specialized instructions can also be included into our code. Usually we need to provide some kind of extra flag or an option out there to link that code into our program. So what that means, in other words, is just the compilation step that we talked about, which takes our code, what we wrote, and converts it into object code, assembly language or object binaries, right, is only one small part of the process. You then need to link that together with a whole bunch of other libraries out here and generate a larger binary code once again, right, but which contains a lot more detail than what you started with. The idea over here, of course, is for the most part to reuse existing code. Each and every person who writes a program for a processor should not have to reinvent the wheel and rewrite, for example, how to create the printf function, right, or for that matter even the sine or cosine functions and so on, right. It should be possible to reuse code that somebody else has already written and optimized for the system that you have. So what the linking process does, it basically takes user code which you have written, library code which could be, for example, sine, cosine, which you have linked in explicitly using the -lm flag to include the math library, and certain other libraries that are part of what's called the OS runtime. OS is the operating system, right? And it basically creates something called the runtime, which is again a set of libraries, a set of functions that have been pre-compiled and are ready for you to use. What the linking process does is it takes all of these together and creates a single object or a binary image, which is something that the system that you are trying to use in order to run knows how to deal with. It knows what to do with this particular set of files, right, and how to actually load it into memory in such a way that it can now get executed as a program. So in order to do this linking process, we need to actually specify some information, and what I'm going to do now is to show you something called a linker script, right. So this particular file that I have got open on the screen over here is something called a linker script, right. As you can see, this is basically, it was created for the STM32, the cube IDE that is used over there, and it also gives you a little bit more information saying that it's a linker script for the STM32C031 member of the family, right. Now, similar to what you have in C programs, this thing, anything starting with a /* and all of these lines after it until you end up with a / again is basically comments, right. So everything that you are seeing out here is basically a set of comments that are explaining what this script is about, right. And the good thing about it is it basically means that, you know, all of this is primarily there for documentation. It's telling you a little bit more about the copyright, it tells you a bit more about what the context of this particular script is and so on. But what we are interested in, of course, is the actual script itself, right. And you can this is not a language that is easy to understand like C or other kinds of programming languages. It is in fact not even a complete programming language. It is not meant for writing programs, right? It is meant for specifying a memory layout. And why is it that you need to know about a linker script, right? Because there are pieces of information out here that tell you a lot about how the memory inside the system is going to be used, right? And in certain cases, especially when you are dealing with highly resource constrained microprocessors or microcontrollers, this information becomes important. It sort of tells you whether or not your program can even fit within memory. And if it does not fit within memory, what are the things you can do in order to change that and possibly make it fit, okay? It specifies something called the entry point, which the entry point is basically telling you about what is the function that is present in your entire code to which the system, whether it's the operating system or whether it is something else that is actually causing this program to get loaded and run in this on the actual processor, needs to initialize the program counter, okay? Reset handler in this context basically refers to a function, right? Who wrote this function? You could write it if necessary, but in general this is something that is written as part of the runtime, which are a bunch of other functions that get added on to whatever code you write, and finally an executable is created. So there is some function called a reset handler, and what this says is that when you are actually going to be executing this program, reset handler is the point at which the system is supposed to start. It has a few other pieces of information such as the the size of the stack, what to do with the so-called heap and stack and so on. For the most part, again, you don't really need to worry about these things, but there are interesting things which basically say that, for example, the minimum size of the heap and the minimum size of the stack are this much, right? So what is 0x200? It's a hexadecimal number. So 0x200 in this case probably is a value of around 512 bytes, right? All that it's saying is the minimum heap size is 512 bytes. This is really small, right? I mean, typically when we do malloc, it's for usually thousands of bytes. So if you have only half a kilobyte of space, then you probably can't really allocate any significant amount of dynamic arrays, right? But keep in mind that this is just the minimum requirement. All it says is that if you don't even have this much, you are likely to run into problems when you actually try to execute the program, which means that the linker itself will sort of give up and fail if you are trying to generate a program where there isn't even that much memory. Now, how could that happen? Well, because of the fact that the linker's job is also to take all the other code that you as well as the operating system runtime and so on are providing and to put them into the text part of your memory layout, create all the initialized data variables, uninitialized data variables and so on, and set apart space for those, and then finally say, okay, this is where the heap is going to be, and then the stack, right? So these kind of minimum values are more sort of sanity checks, saying that if you don't even have this much, it's not going to run at all, right? And now here is the interesting part. It basically tells you a little bit about the actual memory that is present inside the ARM Cortex, the STM32 series. And these numbers are actually telling you something very specific. It basically says that there are two types of memory. One of them is called one part of memory is the RAM, which is what we usually think of as the actual read-write part of memory. And as you can see over here, it actually specifies that it is XRW. What does that mean? It means that code that the numbers that are present here can be treated as instructions and executed if necessary. Right? That is what the X stands for. The R means you can read it, and W means you can also write it. There is also another part of memory called flash, which is not meant to be written. It's only R and X. Okay. It also says what the origin addresses of those locations are. Right. So for example, it says that by starting at this particular address, which is 2 followed by 7 zeros of hex, you are basically going to be addressing the RAM, right? And if you remember our discussions of memory maps, basically what it says is that the RAM starts at this particular origin address and it has a length of 12 kilobytes or 12 into 1024 addresses. Flash on the other hand has a different starting address, right? It is 8 followed by 6 zeros in this case and a length of 32 kilobytes, right? So effectively what it says in other words is that when you are finally creating the program that is going to be installed into the main memory, you need to take these numbers into account. The flash needs to start from this place. So your code should be written such that it actually starts from the beginning of flash and occupies a certain place in memory. And then there would be something else which actually takes care of the fact that when you're running it, perhaps the variables that you need cannot be in flash because you can't write into them, right? They need to actually be loaded into RAM. All of that is specified as part of this linker script that we have over here, and that happens in the so-called sections that we are seeing below, right? So what are these sections? Basically, if we go down over here, let's ignore this part about ISR vectors for now, but the first thing that you can see in this comment is that this is basically some startup code, okay? It sort of tells you how to actually initialize the processor. This is something which usually you as the end user are unlikely to write unless you are actually designing a new processor or a new kind of system. And this code basically needs to go and sit in the flash memory. And now we can see those words that we talked about earlier, the .text, right? So the text is basically going to be where the program code goes, and this goes into flash, right? And there are a bunch of things which sort of talk about how the alignment should be and what are the other kinds of things to do over here. For the most part, just ignore it, right? What is important is that it basically says there is such a section and that it goes into the flash memory, right? After that, there is also the read-only data, which once again also goes into the flash memory, right? There are a few other sections like pre-initialized arrays and so on, which we are going to sort of ignore for now. There can be many different sections that you create as part of a linker script, right? And what is interesting for us though is that there is this part which says that there is a .data, right, which is another one of the sections that we talked about earlier, and that needs to go into RAM, right? But it also starts off by being in flash. So in other words, it basically gets copied from the flash into the RAM, right? So there has to be something that there has to be some initialization code that is going to take it from the flash where the initialization values are present and put it into some location in RAM, right? So what does this mean? It means that the .data will basically be assigned some kind of addresses which are in the RAM area of memory. So if you ever declare a pointer over there and you try to look at the value corresponding to a pointer that you have, you will find that it corresponds to the RAM part of memory. And then once again you have the uninitialized data which goes straight into RAM. It does not have to even be in flash simply because there are no initialization values that you need to load. All that it's telling you is if there are variables that have been defined but not initialized, you have not specified what the value is going to be, they then need to have space set apart for them in the RAM, right? And that's all that you need to do. You don't need to actually initialize them to any known values, at least not as far as the linker is concerned, right? And then finally you have the heap and the stack, which are also going to end up in the RAM, right? And what it does is it basically uses those values that you specified, the minimum heap size and the minimum stack size, in order to make sure that there is something out here, that there is enough space for what for at least creating a minimum sized heap as well as stack that the program can then use in order to execute. So once again, what does this linker script do, right? If we go back and look at this diagram out here, what it has specified for you is to say that this part of it, the text, should start from the beginning of flash. In other words, that address 8 followed by 6 zeros. How much space should it occupy? Well, that depends on how big your program is. So the linker is going to take all the code from your program as well as all your other the runtime functions and so on, like printf and various other things that you might be using, right? And put all of them together into the flash part of memory, right? Read-only data can also go into flash. This data, which is initialized variables, has to be in flash because I need to know what values to initialize them to, but at some point is going to get copied over into RAM. The other parts of it, such as the BSS and the heap and stack and so on, go directly into RAM. The linker just needs to know that I need to create space for these, right? Not necessarily to actually just run them from flash. Okay, so if you do encounter a linker script, and at some point as you go through embedded systems development, it is very likely that you will need to sort of be able to interpret them and possibly modify them. This is what is being done by the linker script, right? It sort of specifies the memory layout. The actual program called the linker then goes ahead and takes all of this and creates a final executable file which satisfies all of these conditions. As an example of that, so as an example of the final output that gets generated after linking process, right? What is usually generated is something called an ELF file. ELF stands for the extensible linker format, right? So clearly it is the output of the linking process. And what is done in this particular case is that we basically have taken the code that we wrote as well as a bunch of other functions, right? And created a final executable. Now, in this case, the code that I'm going to show you the final executable for corresponds to the code that we used when we wrote the C program for the blinking LED, right? The code itself, we can take a brief look at it. So the code that we are looking at to see what the final ELF file looks like is the code that we used in order to make this LED blink, right? And as you would recall, it basically consists of two primary functions. There is something called the init GPIO, right, whose job was to initialize certain GPIO variables, and then there was another function called toggle pin, right, whose function is basically to toggle the pin connected to the LED. The main function by itself basically calls init GPIO and then basically goes into a for loop where there is a delay followed by toggling the pin, right. Now, what I'm going to show you is what happens when this code is compiled and finally linked in order to create a target executable, right. So the first thing is the result of the compilation, right. The command that I use over here is objdump, right, but you can see that the command that I'm actually typing is arm none eabi -objdump. Now that's because the objdump command by default refers to what I'm actually using on my system, which in this case happens to be an x86 based processor. So I need to specify that I want an object dump program which can understand ARM assembly language and can do an object dump for that. Don't worry too much about what the none and the EABI stand for. They are part, or they basically refer to the fact that there is no operating system involved over here. But what is important for us is that it's able to disassemble. This -d flag stands for disassemble an object file, in this case main.o. Okay. So when I look at the result of disassembling in this way, what ends up happening is that I can see that it basically tells me that this is the disassembly of the .text part of this particular program, and in fact it sort of breaks it up and says that there's a .text .init GPIO which has been given a label init GPIO, and if you look at it, you'll notice that it starts from address location number 0 and gives you a bunch of instructions out here. Okay, it also tells you what those instructions are. There are some move instructions, LSLS stands for a left shift, LDR is to load into register from memory, and is basically an AND operation, right? And if you look carefully through this, what you will be able to do is that you can actually identify that this basically corresponds to the masking operations that we applied in the init GPIO. That's where the AND operation is coming in. So if you look carefully, you can find out exactly what it is that was being done in terms of the masking operation and how it is that we are able to select a specific bit and mask it out. Okay. Now, as you go further down, you will find that there is another section which is called the .text.toggle pin. The operations over there are similar. There is something which moves something into a register. There are some shifts, ANDs, which is basically bit masking. There is a BICS assembly language instruction, which is basically a bit clear, which is used in order to clear or set to 0 a particular bit value, right? So rather than doing masking, in this case, what it does is it explicitly just converts a particular bit value into 0, right? Or it can use it in order to set something else to 1. Now, one thing you should notice over here is look at the addresses that are there for toggle pin out here. Once again, it starts from 0, right? Which doesn't seem quite right, because after all, we already had another function called init GPIO which also started from 0. I can't have both functions starting from 0. And finally, I find that I also have a .text.main, which once again starts from 0, right? And has a bunch of instructions which, if I look carefully at it, I can sort of interpret that, this is first calling init GPIO, then it's calling toggle pin, then it's running a for loop, and once the for loop has completed, right, it is actually going to go ahead and call toggle pin again, all in an endless loop. Okay, but and so it looks good. Basically, the code that I wrote seems to have got translated into a bunch of assembly language instructions that I can at least identify, and they sort of seem to make sense in terms of what I wanted to do. The problem is all of them seem to be at address location number 0, right? So what do I do about that? That's where the linker comes in. And what we can see is that it has actually created a final file called an ELF file. Right? And if I run the same command, which is the objdump, directly on this file, which is called the ELF file out here, and let's take a look at the result. Now suddenly it starts to look a little different. One of them is it just says disassembly of the section .text. It no longer says .text .function name. In other words, it has already created one .text corresponding to the entire program that we want. The other interesting thing is you will notice that the addresses are now looking a little different. It starts from address 8 followed by all these zeros and then something C0. Okay. Why not from 800? Because the first few instructions are used for certain other things in order to actually have some data corresponding to interrupts and various other things. Okay. But now the addresses actually seem to have got resolved and are no longer just sort of local to each individual function. But more importantly, you can see that there are some functions here that I don't recall writing, right? And it turns out that all of these functions are part of the runtime and are automatically included by the linker. If you go through it, you will find that there are a whole lot of them, right? Until I finally come to my init GPIO function. Then I have my toggle pin function, and you can see now that each one of these has got a very precise location in memory, right? The main function also has its own address that has been assigned to it, right? And after that, suddenly I have a whole bunch of other functions again, some handlers, some other thing which is the inktick, GPIO, EXTI, there's something called system init. All of these are actually functions. Where were those functions defined? They were defined as part of the C runtime, right? And the linker automatically takes all of those functions as part of the runtime and combines them together into one final executable, which is what you see over here. It knows the order in which to put them together. You can specify that order as if you are explicitly calling the linker, except that usually we just call the GCC compiler, and one of the steps that it does is to also call the linker and tell it, okay, create the final ELF executable for me. Okay. So what you can see over here is that now this seems to have a lot more detail. It has in fact got everything right up to the point where there is the finish part of the code, which tells it that this is also at some part of the flash memory and basically contains everything that is required for this program to run. Which means at this point I should actually be able to take this ELF file and somehow load it into the memory of my system, jump to location 800 whatever it is, and from there onwards I should find that there are instructions that I can actually execute, which will actually run my entire program for me. Okay. So the linking process, in other words, has created something which can finally sort of be taken and put into the memory of the system and should hopefully run the way that we expect the program to. Now, there's just one question that's left as far as the linking process is concerned. We know that the linker can create an executable, a binary file which contains all the instructions that we need, along with information about which addresses they need to be placed at. But somebody or something still has to take those things and put them into the actual physical locations in memory, right? And that is usually done by something called the loader, right? The command that is used in Linux systems at least is usually something called LD, which works as a combined linker plus loader. It creates the linked file for you, but also at runtime, that is when the operating system actually invokes a program, it also takes care of loading that program into memory, right? When you have an operating system like Linux or Windows or Mac OS, they take care of loading the program into memory. When I type in a command or I double click on a program, what's actually happening behind the scenes is the executable content, the ELF file corresponding to that program, is first read from disk, and some part of my operating system, which is related to the loader that I have, takes the different parts of that ELF file and puts it into different parts in memory, right? So that I have allocated enough space for it. And once I have done that, that loader jumps to the first instruction present in that first memory location and says, okay, now you take over. Okay, at least this is the story at a sufficiently high level of abstraction. There are details over there that you can only get into when you start to understand what operating systems do. But to a good first approximation, this is actually what happens when you try to run a program.